Okay, now we're going to talk about the range space and the null space, and we're going to find that these actually tie into some concepts that we already know. Remember, we talked in the matrix, we talked about row space and column space. So here we're also going to associate spaces with a linear transformation. We know that a matrix defines a linear mapping. So we're going to generalize some of these concepts in terms of linear mapping. And you'll see how we define these spaces in terms of the properties of homomorphism. Okay. All right, now, under homomorphism, this is the first lemma we're going to prove. Under a homomorphism, the image of any subspace of the domain is a subspace of the codomain. So let's draw a picture here. We have V goes to W. Okay. And I have some subspace in here. I always think of subspaces like a plane. Okay, and that's going to map to something over here. It might not map to a plane, it might actually map to a line. But it will map to some subspace of this vector space over here. So if this is a subspace, I'll call that V prime. V prime will map to a subspace of W prime. So if the zero vector is here, you're also going to have the zero vector on here. Okay. All right, the proof is actually pretty straightforward. Suppose we have a linear map. The whole idea is also this whole idea about being closed under linear mapping. Okay. So let H be a linear map and let S be the subspace. So he's actually choosing this subspace here to be S instead of V prime. And this mapping is H, and then he has H of S over here. Okay. So if we take two vectors in S, V1 and V2, to show that H of S is a subspace of W, we only need to show that it's closed under linear combinations of two vectors. Okay, so all I need to do is be able to take two vectors in here. Now, if I have two vectors in here, I can write these two vectors as H of V1 and H of V2. And if it's closed under linear transformation, and if it's closed under linear combination, all I need to do is show that C1 H of V1 plus C2 H of V2 is also in H of S. But that's quite straightforward using the linearity property. If I take C1, I'm sorry, he uses S1 and S2, so we'll say S1 and S2 as his two vectors here. So he's taken two vectors S1 and S2. And H of S1, H of S2. So just to recap, to show that H of S is closed, I only need to show that H of S1, linear combined with H of S2, is also in H of S. Okay. And that proof is here. Same proof we've seen many, many times. The linearity property allows me to put the constants in, and I know that this vector here is a linear combination of the vectors in S, and by hypothesis, S itself is a subspace. So this is actually equal to H of some vector in S, so it's actually a vector in H of S. Okay, right, follow it through a few times. The idea is there. So here's an example. If I have rotation, and for instance, if I have rotation, I could take a line in the domain. Now, when I rotate that line, it's going to turn into another line. Okay, so this subspace, this line, which is a subspace, maps to another subspace, which is another line. Okay. Another subspace that's associated with homomorphism is called the range space. So I'm sorry, so we're using this previous lemma to define the range space, which is in fact I can think of the range space of a homomorphism is exactly the set H of V. It's the set of all vectors in W that are images of vectors in V. So we showed in that lemma that in fact this is a vector space. Okay. The dimension of the range space is called the rank of the homomorphism. We're using here homomorphism and map interchangeably. Okay. So here's an example. Take a projection. Okay. And you can see actually, if you think about it, this projection mapping R3 to R2 is going to be an onto map. So the range space is actually all of R2 itself. Okay. And then since this is a two-dimensional vector space, the rank of this projection map is 2. The derivative map, okay, it maps from R4 to R4, but it turns out that, well, here you shouldn't say R, you actually should say P4 to P4 is what should be here. Okay. If you think about the range of this mapping, actually the range only goes up to third degree polynomials because the derivative of x to the fourth is x cubed. Okay, so in fact the range of d dx is equal to P3 in this case. All right, so in fact the rank of the derivative function when acting on P4 is 3. Now if you had the derivative map acting on a P5, then it turns out the rank of the function would be 4. The rank of the map depends on the domain that it's being acted on. Okay. All right. If I map this mapping from the 2x2 matrices to R2, I'm adding the rows together and getting a two-dimensional vector from a 2x2 matrix. And suppose I take the range space. Let's see. So the range space of this mapping is this line through the origin. Okay, because it turns out that any matrix is going to map to an element on this line. Okay. So I'll let you check that. All right, so here we want to talk about this concept that homomorphisms organize the domain. So what does that mean, homomorphisms organize the domain? Remember we've talked about equivalence classes. It turns out the homomorphisms organize the domain into equivalence classes. Okay, so if you have your domain here, then in some sense the homomorphism is going to break this domain up into classes, and in fact each one of these classes is going to be associated with a unique element of the range space. So all of the elements in the domain in this class map to an individual in the range space. All right, that's kind of vague now. We'll see several examples to show how that works. Okay. All right, so consider the effect of dropping the one-to-one condition. Remember that homomorphisms are no longer one-to-one. Now, for some vector w in the range, there may be many vectors v mapped to w. Okay. All right, so he's trying to show that here by showing that all of these individual elements of v map to the same element of w. So here we have 1, 2, 3, 4, 5 elements of v that map to the same element of w. Well, there may be more elements of v that map to w. He's just showing 5 of them. Okay. Recall from your discrete math or other class that for any function h from one space to another, the set of elements of the domain that map to a particular element in the range is called the inverse image. Okay. This is the mathematical definition. H inverse of a particular element can be a set. It's not necessarily an individual element. So it's the set of all vectors v in the domain that map to that particular element in the range. So in this case, if this was W1 here, then this group here, that would be H inverse of W1. And similarly for the other ones, W2, W3, this would be H inverse of W2, and so on. Okay, let's do an example. Take the projection map from R2 to R1. Okay, so I can draw a picture of that. Here's R2. The projection map means that I map any xy. I'll project that onto the x-axis. So this vector here is always going to map to a vector along the x-axis. Right. So we can identify the codomain with the x-axis, as I just said. Here's a member of the x-axis outlined in red. Okay. So this is one particular element in the codomain. Now remember that H inverse of this particular element is the set of all vectors in the domain that map to this same element in the codomain. Okay. Now if you think about it, all of these points in R2 will map to this same element in the codomain. Even so, you can say all of these points are inverse images of this single point on the x-axis. Right. And in fact, if you take any linear combination of these inverse images, it will also be an inverse image. Okay. Definition of addition preservation is that pi of u plus v equals pi of u plus pi of v. Therefore, where pi of u equals 2 and pi of v equals 3, the vector sum u plus v will be mapped to by pi to phi. Okay. All right, so we can see, in fact, that these vectors here, if I take a linear combination of these vectors, they will not map to the same. They will not map to the same vector here. Okay, we can understand the definition of addition preservation as red plus blue makes purple. A 2 vector plus a 3 vector sums to a 5 vector. Okay. The same analysis holds for any homomorphism. So the projection from R3 to R2 is a linear map. As above, we can identify the codomain with the xy plane inside of R3. Okay, this R2 can be identified as the xy plane. Okay, all right, in the xy plane, red plus blue makes purple. Okay, so that's W1 plus W2 equals W3. Now, if I take, the point here that he's trying to make is if I take any vector in the inverse image of this vector here, and I add that to any vector in the inverse image of this vector here, that will get me another vector that's in the inverse image of this third vector here. In other words, you can say that addition down in the codomain in some sense lifts to addition in the domain. Okay, so any point in this, so I think he's going to make this picture more clear. Okay, so if I have V1, V2, V3, so here I have V1 is in H inverse of W1. I have V2, which is in H inverse of W2. And V3 is in H inverse of W3. And in this case, I have W1, W2, W3. W1 plus W2 is equal to W3. And so in a sense, I can say something like this: H inverse of W1 plus H inverse of W2 is equal to H inverse of W3. Now, that isn't really valid because you don't add sets in this way, but this picture is supposed to show you that in some sense there is a correspondence. And I think we'll make this more precise shortly. All right, this also holds in spaces that are not ones that we can conveniently draw. Consider the function from quadratic polynomials to R2 that maps this polynomial into this vector. Okay, notice that this image vector only depends on the linear coefficient. And consider the following 3 members of the range. Okay. Okay. Now, what's the inverse image of this first vector here? Well, notice that the mapping does not depend on A or C. So any polynomial that's ax squared plus x plus c will map to W1. Any polynomial that's ax squared minus x plus c will map to W2. Any polynomial that's ax squared plus 0 plus c will map to W3. Okay, so here are some examples of vectors that map to W1. Similarly, W2, as I said, this W2 is going to be all quadratic polynomials that have a minus x. In other words, they have minus 1 for the coefficient of x in the polynomial. The set of vectors that are inverse images of W3 will have 0 for their linear coefficient. Any vector in H inverse of W1 plus any vector in H inverse of W2 will be equal to a vector in H inverse of W3. Okay. If I have a polynomial that has a linear term x plus a polynomial that has linear term minus x, that's going to give me a polynomial with linear term 0. Okay. In each of these examples, because there's a homomorphism from V to W, we can view the domain V as organized into the inverse images. And it's organized because these inverse image sets reflect the structure of the range in that a W1 vector plus a W2 vector is equal to a W1 plus W2 vector. It may take you a little while to wrap your mind around that concept, but if you go back to the picture and work through that a couple times, I think it will become clear. Now, let me talk about null space. I'm going to stop here for a minute and we'll start up with the next video.